Okay, here we go. It's our first coronavirus lecture. We're going to pick up right after Chapter 8 and go into Chapter 9. Chapter 9 is pretty intense. It's about aerobic respiration. It's all about the mitochondria, all about energy, all about what goes on there. Of course, it starts with glucose and it ends up with CO2. And there's a lot of things that happen in the way. So we're going to pick up with concept 9.1. That's the beginning. Chapter 9, concept 1. So this part is really about getting energy from organic fuels. This is kind of an overview, a lot of important things. Getting energy from organic fuels. And I guess it all starts with the nature of energy in chemical reactions. So before, we talked briefly about redox reactions. So we call these things redox reactions because they're oxidation reduction reactions. Redox reactions, very important concept. The idea is that there is an oxidation which is the loss of electrons from one substance. And then we have a reduction. And the reduction is the addition or gain of electrons to another substance. Of course, the key here is that we've coupled this from and to. It's the concept that these things are always coupled. Something gets oxidized, something gets reduced. So redox reactions are really important. I think one way to look at redox reactions in a very simple way is to take a look at an example of an ionization phenomenon. So if we take sodium, you know that one, and we take chlorine, the reaction would be this guy gives an electron to this guy. So we end up with sodium plus Cl minus. So I guess you could take a look at that and see that the sodium here got what? It lost electrons, so it got oxidized. So sodium becomes oxidized. And then the other one is that chlorine becomes reduced. So check it out. Sodium became oxidized, chlorine became reduced. An electron was transferred from here to here. A loss of electron is an oxidation. A gain of an electron, shown over here, is a reduction. And the best way to memorize that is, of course, that negative and reduce, they go together. So to gain negativity is to be reduced, right? So there we have it. So you've seen this before, but it's really important for us because what we're going to do is take a look at redox reactions in the big picture. So I'm going to erase the board and we're going to throw up the big picture. We're going to start with glucose. So here goes the big picture. We've got C6H12O6, your friend and mine, plus 6 O2, oxidation. And you'll see this arrow, but there's a whole bunch of steps in this arrow. So I'm just going to put a whole bunch of arrowheads like I've done before. This indicates many steps, many reactions. It indicates sequence of reactions, and that's super important. So here's glucose, your friend. Here's O2, and we're going to take that over to the other side, balanced, which is 6CO2 plus 6H2O. That's the big picture reaction then. It's really a whole bunch of reactions. And in this process, we can do just what we did before. We can see that glucose, the carbon really of glucose, I guess we could, this becomes oxidized. And we can look at, likewise, this becomes reduced. Now, this is just a grand simplification. This exact story was presented in the textbook. It's an oversimplification because, as I mentioned, there are many, many discrete reactions here, but in the general process, we have an oxidation phenomenon and a reduction phenomenon. Coupled reactions. The next thing we need to do is identify, this is glucose. I think in the simple sense, we should call this glucose fuel. And we should identify that there's other kinds of fuels as well. So we have fuels that are available here. We have glucose, of course, and other carbohydrates, and we have fats. And I guess I'm just going to say et cetera. There's a lot of organic molecules that are fuels. The key thing about fuels is that fuels have lots, they have lots of CH bonds. Carbon-hydrogen bonds. Huge. They have lots of CH bonds. And these fuels are going to be, fuels are oxidized to become things that have lots of CO bonds. Now, you can even begin to see that right here. You can see that glucose CH bonds, if you drew that beautiful structure of glucose, which you all know how to do, you would see lots of carbon-hydrogen bonds. And then, obviously, by the time you get over here, there's nothing but carbon-oxygen bonds. That's all you can make out of CO2. So, lots of CO bonds, lots of CH bonds. That's the process. All right, so now that we've got that, we have to add the last piece to this equation. So I'm going back up here. The other part is, actually I'm going to make that stand out in a different color. This is energy. And wow, what is energy? Heck, we just spent a whole chapter talking about energy, and we're going to talk about it more. So energy, in this sense, is going to be released as electrons. The energy that we're talking about here is going to be released as electrons. I don't know if you remember, but the first week of class, we were describing electrons as pure energy, movement. And that's where we pick up. Energy released as electrons. There's a lot more to say, though. These electrons will actually kind of step down in energy, step by step by step, giving off. Every time they step down, they lose potential energy, which we've already discussed. They lose potential energy every step along the way. And ultimately, I guess I should say every step. And ultimately, what are we going to do? Energy is going to be used to synthesize ATP. Used in the end to synthesize ATP, our guy. And as mentioned, we always have to identify and celebrate our ATP with our big pal, ATP. Okay, so that's the energy story. All right. The really cool part about this, and this, that relates to some concepts, is that if we're getting energy out of the deal, we're going from lots of CH bonds to lots of CO bonds, and then we're getting energy. The only way to do that is one way, in reaction sense. Remember this big concept of, we call this an exothermic reaction. So for the most part, many exothermic reactions are part of the story. The other thing is this part. Remember that if this was the energy of reactants, this was the energy of products, that this guy right here, changing color, this guy right here was the E sub A, the energy of activation. So glucose is not just falling apart. Glucose has, even though the breakdown of these CH bonds to get CO bonds in the big picture ends up producing lots of energy, or yielding, lots of energy from transformation, we end up with, it all comes down to this energy of activation. We've got this energy of activation that must be overcome. How do we overcome energies of activations? Of course, with enzymes. So there's my little dotted line, and we've lowered this activation energy. So this is by enzyme catalyst. Enzyme catalyzed. All right, so now we have to talk about enzymes again. So all of these little steps are going to be exothermic reactions, many of them. There's actually some that are endothermic reactions. You know, you got to do some things. But the net of reactions in this big picture process are exothermic reactions. All of them are enzyme catalyzed to overcome their energies of activation. And we need to talk a little bit about enzymes to kind of refresh our knowledge about what these things are, what they do. Of course, enzymes are proteins. You remember that. You remember that enzymes have names ending in ACE. And then the good stuff that you'll know is that they have an active site. And to that active site, you would know that a substrate binds. Substrates bind here. And you would know that this relationship is specific. What I mean by specific is let's do it, lock and key. Lock and key. So it's a specific relationship, this relationship between the substrate and the active site. All right? And what we're going to see in these reactions is that these enzyme catalyzed steps, we're going to see these enzyme catalyzed steps that are essentially stripping electrons. They're stripping electrons from glucose. Strip electrons from glucose. And we're going to see that electrons just can't be all by themselves. So the electrons are going to travel with a proton. So when we strip electrons from glucose, these electrons will travel with a proton. And a proton, you might remember, is H plus. When an electron travels with the proton, that basically equals an H atom. A hydrogen atom is a proton and electron. Okay, so special stuff here. We're going to bracket these two together. Stripping electrons, traveling with protons, therefore hydrogen atoms. We are going to see all sorts of hydrogen atoms as we go through this process. They're going to be popping up left and right in a lot of the graphics that show this extraordinary process. Hydrogen atoms are really important, but what we need to think about is that a hydrogen atom is a proton with a high energy electron that it got from an enzyme catalyzed reaction. That's a good board. Sorry about the crooked, what can I say? This is the first coronavirus lecture. I gotta kind of get into my stride here, right? So at this point, I'm going to start to get big and deviate. There's a lot of great information in the textbook. There's too much information in the textbook. It's my challenge to actually break this thing down so you can actually understand it and get the important parts. Memorizing all that detail, it might be good in a biochemistry course, but right now we need to kind of see the whole landscape. So all of that stuff about energy and enzymes and exothermic reactions, that's the setup. Now we're going to start to see what this whole process is. The big picture reaction, of course, as I mentioned, was this one. C6H12O6 plus O2, 6 of them, going to form, and again, many arrowheads, many heads, many steps, going to form 6 CO2s plus 6 H2Os. One of these, 6 of these, lots of CH bonds, think CH, lots of CO bonds, and this, of course, is a great oxidation phenomenon. Redox reaction, coupled, all the above. Okay, so this is the big picture for us. We want to identify the players in respiration. So, the players of respiration, the first category, we're going to have 5 categories in total. The first category, enzymes. And enzymes, we have a lot of different kinds of enzymes to get this whole thing done. The bottom line is that we should remember what enzymes do. Enzymes catalyze reactions. So if you took, for instance, an example of an exothermic reaction, and we want to look at it being catalyzed. And catalyzed means to us sped up. We start with a certain free energy level here. We have time on this axis. We've done lots of these before. We have reactants at an energy, and then we have products at an energy. And it's this hill here, this hill that we call the energy of activation. Right there. So that is our E sub A. And as I just showed you just a second ago, what happens is enzymes lower the E sub A. So that is our enzyme catalyzed E sub A. It's been lowered. So the other thing we want to talk about is enzymes is where are they? Where are they in this big system? So to get this whole job done, we're going to have some enzymes that are in the cytoplasm of the cell. And we're going to have other enzymes that are going to be integral. That means that they're in the membrane, if you remember that. Integral in the membranes of the inner membrane of the mitochondria. Mitochondrial inner membranes. And I guess we should just take a little quick snapshot of a mitochondrion. Remember that we have an outer membrane. Remember that we have all these beautiful folds to make the inner membrane. So this is that inner membrane right here. And what we're going to see in the mitochondrial inner membrane are going to be lots of enzymes that are embedded. They're integral in that. And of course, all that great stuff that you should be thinking about. Integral proteins that are nestled in membranes have nonpolar domains, so they can live in that nonpolar part of the phospholipid bilayer. Remember, of course, that this is a phospholipid bilayer called the outer membrane, and this is a phospholipid bilayer called the inner membrane. So all that stuff we've been working on in building a cell, in building organelles, is coming here right now. We're putting it all together. All right, so we got that. Of course, the other things to remember about enzymes: substrate, active site, etc., 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 inhibition of enzymes, all those good things. Related to enzymes is going to be our next set of players, and these collectively are called coenzymes. Now, coenzymes are types of cofactors. Cofactors are defined as non-protein component required for enzyme function. There's a lot of different kinds of cofactors out there. In the case of the ones that get the coenzyme name, organic ones. Organic cofactors are called coenzymes. Inorganic ones don't have a special name, but I wanted to let you know that there are some inorganic ones, and examples of these would be iron, copper, let's see. Forgot another one. Let me get a little tight. For my inorganic ones. Oh, heck yeah, zinc. Iron, zinc, copper. These are examples of inorganic cofactors. Organic cofactors we call coenzymes. We do not call inorganic cofactors coenzymes. That's an example. They also vary in terms of whether they're permanently attached or kind of not. So another definition of cofactor is that they can either be permanently attached to the enzyme, or not so. So I guess they would call, you use words like they're tight, and then not would be loose. Now, it's actually going to be a very special group of coenzymes that are not tightly and permanently bound, that are actually coenzymes that are our big deal. We're going to look at these special coenzymes of NAD and FAD. So we've got these two guys right here. And that's what we're going to spend the whole next board talking about: NAD and FAD, what they are and what they do. So we need to look at NAD. NAD stands for nicotinamide adenine. You've seen that before. Adenine dinucleotide. Wow. So NAD, nicotinamide adenine dinucleotide. Now, just a little snapshot here. A nucleotide, you guys would remember, is a sugar, a phosphate, and a nitrogenous base. Adenine is a nitrogenous base, as you recall. It's a purine nitrogenous base. It's got 2 rings that have nitrogen in the rings. You can draw a cartoon of it, and what happens is that 2 of these hook up together by their phosphate groups linking together, and then on the other end they got this thing called nicotinamide. And this is the part of this coenzyme that actually is going to play a crucial role in our oxidation reduction phenomenon. Nicotinamide. So the whole thing we call NAD, and it is an important coenzyme. What we're going to see in this process, if we take a look at this, if this is a coenzyme, this is something that's required for the function of the enzyme, but it's not the enzyme. And remember that it's the type of a coenzyme that's loose, not permanent. So we're going to come up with a cartoon of this story that is pretty common. So here I'm going to draw something like this, and then I'm going to draw something like this. We're going to identify this as our enzyme. More specifically, I'm even going to tell you what kind of an enzyme, what class of an enzyme it is. This is what's called a dehydrogenase. Any guess what that does? A dehydrogenase? So there's your ASE, that's the enzyme concept. Hydrogen and D, it removes hydrogens. And when hydrogens get removed, electrons go with them, and so therefore that's an oxidation. I guess what we should do is therefore identify NAD as an oxidizing agent. Okay, so here's our dehydrogenase. And then let's draw NAD. So here is NAD, and it looks like it just wants to fit in that site. NAD. As a matter of fact, now we actually have to identify it in the state that it's in. We have to put a plus sign there. This is really, really important. You'll see why in a minute. And then we have to grab, let's go, orange. We have to grab what is going to be our fuel. This thing right here is what we would call our fuel molecule. And this fuel molecule, we're going to point out what it has. I'm going to say more about this to the side here in a second. But this fuel molecule is going to have for instance, it could be glucose. So take a look at this. Here's the glucose. Remember your glucose. So here it is in the ring form, as you do before. And I will opt for an alpha glucose, and I'm actually going to make bonds between those hydrogens. Okay, the reason I did this is I want us to identify all of these CH bonds. You know, look at these things. Matter of fact, I want to identify not only that, I want to identify these groups. An hydroxyl and a carbon with a hydrogen and a couple of bonds. There's one, There's one. There's one. And technically speaking, there's one. Look at all that stuff. So what we can do with these parts here is show them up here in the fuel formula. I'm going to have a bond. I'm going to have a carbon. I'm going to have, let's see, I'll stick a hydrogen on this side, and I'll stick a bond there, and I'll stick an O and an H. So that's what I've drawn here. In whatever twisted configuration it is, it's a carbon with a hydrogen and an oxygen and a hydrogen, so an hydroxyl group, stuck to something else in a chain. So that's going to be our fuel. What we need to do is specially identify the hydrogens, because we need to follow these hydrogens. I don't know if red is showing up very well against orange, but look at that. There's our hydrogens. So we want to follow those and see what happens to them. So this is the whole thing, kind of getting ready for action. And then we could draw an intermediate in the process. So here's an intermediate. Let's draw our enzyme. And in our intermediate, we're going to stick NADH, the cofactor, the coenzyme, in its place. So now it's NAD, and we're going to actually stick one of these hydrogens on this. Show you what's going on here. We also got an we got an electron coming down from here. I'll show you that in a minute. Let's draw it first. So here's our fuel molecule parked in the enzyme. And what we're doing then in this fuel molecule is stripping these hydrogens and electrons off. So C blank blank H O H. So this guy here and this guy here, this guy is going to leave. And it will be an H plus at this point. Then we have one hydrogen here, and the whole way that this happened, what was required for this to happen, was 2 electrons stripped away from this process. 2 electrons were stripped away from this process, so now we have this whole unit here, which I will show in one more frame. This is just kind of an intermediate frame. The whole process after things leave the enzyme. Now we have, still it's our food molecule, but boy is it different. The food molecule now is this. What? Look at that. That's what's left of this thing. So we went from those CH bonds, as I told you before, CH bonds, and we went to this. Major oxidation. Okay. Then, the most important part for us is that what we have here is NAD, whoops, wrong color, NADH. So this is our guy. This is NADH. And we also have a proton plus H plus. I'm not circling H plus. That's an ion. I'm circling a hydrogen that actually has an electron associated. So there's actually 2 electrons here. There's 2 electrons in this party. They're right there. That is just huge. I think some people like to think of NADH as an electron carrier. So NAD, an electron carrier sometimes. I've even referred to it myself in this way, an electron taxicab. Both of these names, carrier and taxi, imply that this thing is going to take electrons somewhere else. This is the big deal. NADH has electrons, this precious cargo right here, and it's going to take those electrons somewhere else. Those electrons are energy, and those electrons are going to be used for something. So that is the big picture to set us up. Okay, so our first cofactor, of course, which is a coenzyme, is NAD. I'm going to continue and just kind of list the other two just by name, so we know what they are when they show up. All right, so if you see where we are, that was a crazy insert, but we're still in number 2 with these things called coenzymes, which were types of cofactors. NAD, of course, that's our first one. Just going to kind of summarize what NAD is. NAD plus goes to form, we'll add in NADH. So if it goes this way, we're going to bring in 2 electrons, and we're going to bring in, technically, 1 net H plus is what we're going to carry. So I'm going to put H plus there. Because remember, the other one is over here. So I guess I could do that. So 2 H pluses. And then coming out, this thing is reversible. So that's the NAD story. So this is the taxi cab that has passengers. This is the taxi cab that sign is on, ready to pick up. The next one is a very similar entity, a coenzyme called FAD. And FAD is going to look like this. FAD, FADH. The catch here is that you've got 2 hydrogens here. And this one is going to be 2 electrons. So going this way, electrons in to be carried. And 2 H pluses. And that's how this one works. That's FADH2. We have another coenzyme that's going to show up later. That's very important. It's got a great name too. There's an enzyme called CoA. So this is coenzyme A. And coenzyme A is an extraordinarily beautiful molecule. I almost feel like I should draw the whole thing just to blow you away, but heck, what the heck, let's see. We got the time. We're gonna see acetyl-CoA. I promise that I will wait to draw coenzyme A when it has an acetyl group stuck on it. So look for a drawing later. So coenzyme A is going to be very important. It shows up, it's not in this class, it's a different function. You're going to see what that function is later on once we get into breaking down glucose. So that's our second category of players. And we've got 3 more categories before we understand all the players that are going to be involved in aerobic respiration. The third one, I've got room for right down here. The third category of players is substrates, right? So we're going to have a lot of things throughout this process that are going to be substrates that are then going to go through an enzyme catalyzed reaction to become something that will be a substrate for the next reaction, and so on and so forth. So the substrates, of course, would include glucose, and then I would say on down to the final product of CO2. So glucose is our big guy. This is our starting substrate, but boy oh boy, there's going to be a lot of substrates as we work our way down. I think we need to identify as players in this process, basically our cellular energy. And I think what we need to identify is basically ATP. Remember, ATP is going to be a player in this. And again, we always want to identify energy is big and powerful and up at the top. And then energy can give off ATP can give off energy by breakdown to form ADP plus inorganic phosphate, and that is energy that can drive an endothermic reaction. And then of course it takes an exothermic reaction of some kind to drive the synthesis of ADP from pi. We're going to talk about this in a minute. And then we're down to the next step we can't forget about, which is to monophosphate. Same deal. Exothermic energy fuels that, and same deal, driving reactions. So the coupling of reactions, energy, this is the way it works. But really, the most important thing is that this whole story of glucose to CO2 is really going to be all about ATP. That's the whole story, is making ATP. We need to understand the fundamental steps and processes that take us to this, from glucose to CO2, and in the process, energy transformation to this chemical state called ATP, because that's the energy of life. This drives our processes. So just remember cellular energy, that's our fourth. And what I want to do at this point is introduce two incredibly cool concepts about how ATP is going to be made. So, ATP synthesis then, we're going to see actually two ways. So maybe I should say there's two fundamental ways in this process that we're going to look at. Again, always make it stand out. It's huge. So ATP synthesis, there's two ways. The first one of these ways is what we're going to call substrate level phosphorylation. And that's a great name. Phosphorylation is adding a phosphate. We've already seen this. Remember the sodium-potassium pump. We had phosphorylation, we had dephosphorylation. And that pump was changing shape. Substrate level phosphorylation, there's a nice picture in your book that describes this. You can go look at it yourself, figure 9.7, page 169. And the idea here is that we have a phosphorylated substrate and a special enzyme. So here's an enzyme, and here we have a substrate. And that substrate has a phosphate stuck to it. And then what we will park here is ADP. So there's ADP, there's the enzyme. Basically what's going to happen here is this phosphate's going to be transferred to that. And by the time the whole process is done, you have an enzyme that's finished. You have a substrate that's left. And then here you have ATP, which I still need to indicate. That's substrate level phosphorylation. So I'm going to point out in the process where this happens and what it looks like. So the second one is called oxidative phosphorylation. Now, the oxidative part is referring to the process of all of these steps from glucose on down. These fundamental steps are oxidations, and they are therefore releasing electrons. So that's why they call it oxidative. So basically, this is going to have to do with loss of electrons. Loss of electrons, and it's going to be those electrons that we're going to use to drive a process of phosphorylation. And we're going to drive it with a really impressive piece of machinery. See, figure 9.14, and this is on page 175. All right, so I think this is a really good time for us to take a look at ATP synthase. This is an extraordinary thing. It's a massive protein that's made up of a whole bunch of subunits. Let's take a look at this figure and get our bearings. So here we see the inner mitochondrial membrane. Of course, those are phospholipids, so it's a phospholipid bilayer. We're very familiar with phospholipid bilayers. This space here is the intermembrane space, which means, of course, that there's another membrane off screen, way up high. And then down here is the matrix. So when we were drawing cartoons of this enzyme, we drew this big flask shape down into the matrix. And that's how we will continue to draw cartoons of this thing. It's kind of a flask with a bulb here. Let's take a look at these parts and kind of put together how this thing works. So this structure here is called the stator. And the stator, that name implies no move. That's not a moving part. So it's stuck in the membrane, this big part here. This is also rigid and doesn't move. And these parts, these are channels. That is half of a channel and the other half of a channel. They don't move. This stuff here in this bluish color, however, some of it does move. Specifically, the rotor moves and the internal rod that's attached to the rotor moves inside of the catalytic knob, which, as you can see from the arm of the stator, is held in place and does not move. So what causes the movement? It kind of looks like a watermill, but it's really not that. H plus is going to move from high concentration in the intermembrane space. Remember, we've been pumping hydrogen into the intermembrane space in all these steps. So we have a concentration gradient, high concentration of H plus here, low concentration of H plus here in the matrix. So the H plus ions move through the first half of the channel. They have a pocket in one of the proteins of the rotor. There's a whole bunch of proteins that are kind of banana shaped, causing a shape change. And every time that shape change occurs, it causes the whole rotor to move. And you get one full resolution, basically, before the H plus completes its journey and enters into the mitochondrial matrix. Of course, this thing called the internal rod is attached to the rotor and spins with the rotor. So we've got a lot of energy down inside the catalytic knob. And it's this energy that's converted into the chemical energy of making a high energy phosphate bond between ADP and inorganic phosphate. Boom, making our ATP. So it's an extraordinary thing. I'm going to post a link to one of the better kinds of high-tech animations of ATP synthase. There's several to choose from, and they get really crazy and really complicated, but if you just kind of look at the thing after building your knowledge here. I think it'll impress. So there we have it, ATP synthase. So here's the more cartoonistic version of ATP synthase and what it does. Specifically, the process is called chemiosmosis. This is how we're going to be making ATP. Remember, the whole thing is titled oxidative phosphorylation. And remember, phosphorylation is adding a phosphate to something. And of course, that's what happens to ADP as it becomes ATP. It gets phosphorylated. So let's take a look at this. This is figure 915 on page 176. And this is called chemiosmosis, which we mentioned, and it's on the board. So back to our formula. This is the intermembrane space, like we saw before. Here's our phospholipid bilayer. This is the mitochondrial inner membrane. This is the matrix, the light-colored part. Now, what we don't really see here is that there should be a whole bunch of hydrogens up here. Many hydrogens up here to represent the concentration gradient of high H plus here, low H plus here. And now they've just simplified the whole thing. This is a cartoon of ATP synthase, which we just saw in much higher detail a minute ago. So here we have our concentration gradient. H plus is driving this process, going down the concentration gradient, and that energy is ultimately converted by energy of motion to chemical energy of phosphorylation of ATP. And, as mentioned, we call this process chemiosmosis. Very cool stuff. So, the general concept of oxidative phosphorylation is that these electrons, this is kind of an overview. The electrons from this process fuel or drive, they drive proton pumps. You might remember that we used the word pump to describe something that used energy to get something across the membrane. So we're talking about crossing a membrane here. So they drive proton pumps that pump H+, from the matrix of the mitochondrion to the intermembrane space, and that thus producing a concentration gradient. And then the process of the enzyme ATP synthase is driven by the movement of hydrogen ions down the gradient. So ATP synthase, which is it's a glorious quaternary protein. We're talking about many subunits and all sorts of crazy things that you'll be surprised to learn about. ATP synthase is then driven by this H plus gradient. So concentrate basically produces ATP. By chemiosmosis, which is the movement of H plus down the concentration gradient. That's it. yeah, you'd say that's it, like that's easy. This is just kind of a narrative, just kind of an overview of the process.